In this video, we are going to learn a few techniques on how to determine the minimum and maximum values of a function. We'll cover the golden section method, the quadratic interpolation method, and the random search method, and discuss a few examples. Towards the end, we'll briefly tackle the method of steepest ascent or descent, as it will be our go-to method when we discuss machine learning. Optimization is the method of finding the maxima and/or minima, or the optimum value of a particular function. In calculus, we determine the optimum value by taking the derivative of the function f of x, setting that function equal to 0, and then determining the corresponding value of x that will make that derivative 0. We determine whether it's a minimum or a maximum by taking the second derivative of the function f double prime of x. If the second derivative is less than 0, then the function is maximum at that value of x. If the second derivative is greater than 0, then that function is minimum at that value of x. Of course, in some functions, you may find numerous optimum values. The x value, which gives you the highest maximum value or the lowest minimum value, are called the global maximum and the global minimum, respectively. All other maxima and minima are called local. We start by defining an interval that contains a single answer. The interval has length L0. We would need 3 function values to detect whether a maximum or minimum occurred. An additional point within the interval has to be chosen. Then we have to pick a 4th point. The test for a maximum or minimum could be applied to discern whether the maximum occurred within the first 3 or last 3 points. We'll discuss this in detail in a couple of slides. 2 conditions are necessary to implement this method. The first condition specifies that the sum of 2 sublengths, L1 and L2, must equal the original interval length. The second says that the ratio of the lengths must be equal. If we solve for L0 in the second equation, and then plug it in the first equation, and then divide everything by L1, we get the first equation written in this slide. If we let R2 be equal to L2 over L1, we obtain 1 plus R equals 1 over R, or the quadratic equation for R as R squared plus R minus 1 equals 0. Solving for R and taking only the positive root, we get R to be equal to 0.61803. This value is called the golden ratio and is the key element of the golden section method. The method starts with 2 initial guesses, xl and xu, that bracket one local extremum of f of x. The next 2 interior points, x1 and x2, are chosen according to the golden ratio. The function is evaluated at these 2 interior points. So we evaluate f of x1 and f of x2. 2 results can occur. If f of x1 is greater than f of x2, then the domain of x to the left of x2 from x1 to x2 can be eliminated because it does not contain the maximum. For this case, x2 becomes the new xl for the next round. If f of x2 is greater than f of x1, then the domain of x to the right of x1 from x1 to xu would have been eliminated. In this case, x1 becomes the new xu for the next round. Then you start over using the new values of xl or xu and repeat the process until xl and xu converges to a single value. That single value is the value of x corresponding to the maximum value of f of x. If you're looking for the minimum, you use f of x1 less than f of x2 in part 1 and f of x1 greater than f of x2 in part 2 instead. Let's consider this example. We have the function f of x equal to 2 sine x minus x squared over 10, and we want to evaluate the optimum value of this function, or specifically the maximum value of this function. We begin by selecting the limits of our interval. We select the lower limit xl equals 0 and the upper limit xu equals 4. We then use the golden ratio to determine d. So we use square root of 5 minus 1 divided by 2 multiplied by the difference of xu and xl. In this example, this will give us 2.472. We then add 2.472 to x1 and then subtract 2.472 to xu. This will give us x1 equals 2.472, which is here, somewhere here, and x2 equals 1.528, which is somewhere here. We then evaluate the function at f of x1 and at f of x2. So at f of x1 equals 2.472, the function is equal to 0.63. And if f of x2 equals 1.528, it is equal to 1.765. In this example, f of x2 is greater than f of x1. This means that we eliminate the interval from x1 up to xu. And we do that by replacing xu with the new value x1. Our new x1 will be equal to 2.472 and xl will still be equal to 0. We then repeat the process using these new values xl equals 0 and x1 equals 2.472. We solve for d using the golden ratio and we obtain 1.528 for d. We then add d to xl and subtract d to x1. This will give us two new intervals where the first interval is from xl equals 0 up to the new x1, which is 1.528. The second interval is from the new x2, which is 0.944, up to xu, which is 2.472. We then evaluate f of x1 and f of x2. In this case, f of x1 is equal to 1.765 and f of x2 is equal to 1.531. So we see that f of x1 is greater than f of x2. So f of x1, which is somewhere here, is greater than f of x2. This means that we have to eliminate this interval here. And what that implies is that we replace xl with the value x2, 0.944. We are then left with this interval. We then repeat the process over this new interval from xl equals 0.944 to xu equals 2.472. Solve for d, we get 0.944. We add that to 0.944 here, subtract that from 2.472 here, which will give us the new x1 and the new x2 respectively. So this is the location of our new x1 and this is the location of our new x2. The first interval is from xl to x1 and the second interval is from x2 to xu. We then evaluate f of x1 and f of x2 and see which is higher, and then from there we can determine which interval to eliminate. So the process is repeated until we converge at a final value for x1 and x2. Let's take a look at the step-by-step results. This table indicates the results for xl, x2, x1, xu, and d for each iteration. The index I corresponds to the ith iteration. So this, for example, corresponds to the first iteration, the second iteration, the third iteration, and so on and so forth. In the first iteration, we have xl equals 0 and xu equals 4. We were able to solve for x1 and x2 using the golden ratio method. And then we compared f of x2 and f of x1. We see here that f of x2 is greater than f of x1, so we replace xu with x1. In the second iteration, xl is still 0, but xu is now the former x1. Then using the golden ratio, we again get new values for x1 and x2. You evaluate f of x2 and f of x1. Compare between these two, we see that f of x1 is greater than f of x2. In this case, we replace xl with this new value x2. So in the third iteration, xl has the value x2 in the previous iteration, but xu still has the same value as before. We again determine x1 and x2, evaluate f of x1 and f of x2. Here, f of x2 is greater than f of x1. Now, we replace xu with x1. So in the fourth iteration, we have xu equal to the former x1. So again, we evaluate x1 and x2 using the golden ratio method, and then also evaluate f of x1 and f of x2, compare which is higher. In this case, f of x1 is higher, which means that we have to replace xl with x2. So we have this new xl here in the next iteration, and the old xu here in the fifth iteration. So we continue on, and you see that xl, x2, x1, and xu slowly converges to a particular value. Now, how do you actually implement the termination, or when do you know when you obtain the optimum value of the function? Once an iteration is complete, the optimum value will either fall in one of two intervals. If x2 gives the optimum function value, it will be in the lower interval xl, x2, and x1. If x1 gives the optimum function value, it will be the upper interval x2, x1, and xu. So looking at the upper interval, if the true value were at the far left, the maximum distance from the estimate would be 2r minus 1 times xu minus xl. And if the true value were at the far right, the maximum distance from the estimate will be 1 minus r xu minus xl. Since the second case represents the maximum error, we obtain an expression that will provide a basis for terminating the iterations. And this is the expression that we're going to use. You compare this error with the tolerance value. For example, you can use a tolerance value of 0.1. If the error gets below this value, then the iteration stops. In this case, the while loop is more appropriate than the for loop. To terminate the execution of the loop, you can use the break command. The while and break commands are both available in MATLAB and Python and are basically the same when executed. Another type of method employed in optimizing a function is called the quadratic interpolation method. This method takes the advantage of the fact that the second-order polynomial often provides a good approximation to the shape of f of x near an optimum. Just as there's only one straight line connecting 2 points, there's only one quadratic or parabola connecting 3 points. The idea is to have 3 points that jointly bracket an optimum, fit a parabola to the points, differentiate it, and set the result equal to 0, and solve for an estimate of the optimal value of x. The result will be the equation shown where x0, x1, and x2 are the initial guesses, and x3 is the value of x that corresponds to the maximum value of the quadratic fit to the guesses. Let's consider an example in the next slide to make sense of all of these. We use the same function f of x in this example and use the quadratic interpolation method on this function. We have initial guesses of x0 equals 0, x1 equals 1, and x2 equals 4. At f of x0 equals 0, we have 0. F of x0 equals 1, we have 1.5829. And at f of x2 equals 4, we have negative 3.1136. The only thing we need to do is to plug in all these values in this equation in order to get the value x3. The next thing that you need to do is to replace x1 with x3. Now that we've replaced x1 with x3 in the previous iteration, we have these new function values. We put in these new function values In our expression for the quadratic interpolation, and we obtain a new value of x3. For this value of x3, we have 1.4903 and f of x3 is equal to 1.7714. We then plug in this x3 here in x1 and repeat the same process. Let's tabulate our results. So we have three initial guesses, 0, x0, x1, and x2. We were able to evaluate x3 and f of x3. We replaced x1 with x3. So now we have x1, x0, the new value of x1, and the old value x2. We evaluate x3 using these new values, and then we replace x1 with x3. We do that over and over again until we get a number that converges towards our optimum value. As you can see, the use of the function to evaluate new values of x makes this method robust and attractive. The main disadvantage of quadratic interpolation is that it can get hung up with just one end of the interval converging. Thus, convergence can be very slow. To terminate the iterations, the same relative error in the golden section method is used. The random search method is a simple example of a brute force method. The method repeatedly evaluates the function at randomly selected values of the independent variables. If a sufficiently number of samples are conducted, the optimum value will eventually be located. We consider this two-dimensional equation in this example. The domain boundaries are -2 to 2 units along the x-axis and 1 to 3 units along the y-axis. The step size is 0.1 units. The idea is to generate values between 0 and 1 using the random number generating function, rand in MATLAB or random in Python. You designate the random number to the variable r. You then multiply the variable r to the domain boundaries along x and along y, and then add the results to the lower boundaries of x and y. You then plug in these new coordinate values, x and y, in the function, and then evaluate whether these new coordinates give you a higher or lower value of the function. If you are looking for the maximum, then you look for the higher value of the function. If it is higher, then you replace the previous coordinates with these new coordinates. If it is lower, then you keep the previous coordinates. This process is iterated for a certain number of times. The more iterations you do, the greater your chances of finding the optimum value. In this example, the optimum value is shown here. X equals -1 and y equals +1.5. If we do the random search method, for 1000 iterations we get x equals -0.9886 and y equals 1.4282. And the function value is 1.2462. For 5000 iterations we have -1.0040 and 1.4724. Notice that for 6000 iterations we get -0.9837 and y equals 1.4936. You can see here immediately the problem with the random search method. The accuracy doesn't depend on the number of iterations. That's something that you have to overcome if you're going to use the random search method. You can see from previous examples that the step size is quite important. At the cost of computation time, you can choose smaller step sizes in order to make your calculation accurate. The method of steepest descent or ascent avoids this problem by determining the direction of the steepest descent or ascent, depending on whether you're looking for the maximum or the minimum, respectively, without having to worry about step sizes or loss or convergence time. We'll discuss this technique in detail when we study machine learning, as this will be an extremely valuable tool. Just to give you a preview of of how the method of steepest ascent or descent works, let's apply the method here in this simple two-dimensional function that we used in the random search method. Maximize the function using the initial guesses x equals -1 and y equals 1. So we evaluate the partial derivatives of f with respect to x and with respect to y. When we do that, we get partial of f of x equals 2y plus 2 minus 2x, and partial of f with respect to y equals 2x minus 4y. We plug in these initial guesses here, y equals 1 and x equals -1, y equals 1 and x equals -1. We get 6 for the partial derivative of f with respect to x and -6 for the partial derivative of f with respect to y. The gradient vector now becomes -6i minus 6j. To find the maximum, we could search along the gradient direction, that is along an h-axis running along the direction of this vector. So the function can be expressed along this vector as x naught plus partial of f with respect to x times h, and then y naught plus partial of f with respect to y times h. This is our partial of f with respect to x, and this is our partial of f with respect to y. Our x naught is -1, so x -1 plus 6h, which is what we find here. And then our y equals 1, so we have 1 minus 6h, which is what we find here. So we evaluate the function at these points and get the new function g of h. G of h is equal to -180h squared plus 72h minus 7. We can directly locate the maximum by taking the derivative with respect to h and then getting a new value of h equals 0.2. So when we get this new value of h, we plug this back in here and here, so we get a new value for x and y, and these will be our new guesses, and we start the procedure again here, beginning from this step. I hope you understand the techniques we've discussed. You can go through the video over and over again and write down your questions. We can discuss anything that is unclear to you in our weekly consultation sessions. Just a small note before we end this video. There will be no exercises on how to implement these techniques in MATLAB or Python. That is left as your task in the machine problem for optimization. Good luck and see you in our next video!